Yeah, so we are very excited to have you here, and we're just going to jump right in. So CS-181, this is the introduction to machine learning. And what we're going to be covering today, or this semester, what we want to do is just give you all a bit of an overview. We're going to chat a little bit about how we got into machine learning, and then we're going to dive into some logistics and some technical content toward the end of the lecture. So what is this course all about? So machine learning, I feel like it gets easier and easier to justify these days. It's kind of everywhere. When I was back in grad school, I couldn't talk to, like, I was working on voice interfaces, but I couldn't talk to the robot. And now, my 4-year-old asks, Alexa, can you fart? And like makes farting noises. Anything from like driving directions to assisting in healthcare applications, all over the place, we see machine learning. We can build like really, truly ridiculously amazing things. But at the same time, and this is going to be an important theme that we're going to carry through the course, is that we're really kind of past the age of just moving fast and breaking things and just building stuff just because it's cool. If there ever was an age where that was appropriate, we've had algorithms that basically pick up the worst biases that we have in our society, that make stupid mistakes because the people who coded them, didn't think through the consequences of the algorithms, and the people who implemented them didn't think through the implications of the implementation. And this has resulted in all sorts of racial bias, bias against people with more severe healthcare conditions, gender bias, all these sorts of things. And today more than ever, rigor. If the algorithm is wrong, and it's distributed over many, many places, that can cause a lot of problems. And thinking about the ethics and the inclusion are really, really essential. So with that, I want to emphasize this, but also step back a little bit and, chat about, some of the fun parts, and, David and I, how did we get into this? So I'm going to stop the share. And machine learning is big. Were you always interested in machine learning?
I never had any idea what machine learning was even, but I do remember the first time that I learned a little bit about what it is. And I was an undergraduate at Oxford. This was, I'll age myself now, this was 1997, before many of you were born, I know. And I was taking a class by this guy, Lionel Tarasenko. Had no idea who he was, but turned out that he'd been working with a company called Sharp, and Sharp had developed a neural network to automatically control a microwave oven. Right? So this blew my mind finale. I was like, really? So not only are we seeing cool mathematics, not only are we seeing activation functions of all different types, but this guy, this Lionel Tarasenko guy, has trained a neural network that is now embedded in a microwave oven. I mean, we'd only just got microwave ovens, and it was supposed to figure out when to stop cooking. And he was already talking about safety issues back then in 1997.
That's good. I'm glad. Yeah.
So that was like the first memory I remember of kind of knowing what machine learning is and being like, oh, this is interesting. What about you? When did you first become aware of what machine learning is?
Yeah. So I mean, when I was in high school, like my high school statistics class was one of those classes that just was like, wow, this is cool. When at least I feel like through most of my education, if you were smart, you were taking geometry and algebra and calculus, and statistics wasn't as emphasized, but I took it anyway. And that was just like, wow. I was also part of the robotics team, but I never connected, statistics and like AI algorithms for like robots and stuff until sophomore year of college. Actually, maybe some of you are in your sophomore year now, where I saw this lecture on particle filters, where the idea was that you didn't know where the robot was, so you had a bunch of places where it could be, and then every time the robot got an observation, it would update, it would cross out some places and say, well, I see a wall in front of me, so I can't be in an open area, and all of these sort of things. And that was just like this moment. I was like, this is like the ridiculously, like, this is the coolest thing ever. It's statistics, it's AI. Look at this beautiful picture. I have to admit, it took me a little longer to get to the the safety aspects and all of that.
That's really interesting that you mentioned particle filters, because I remember the first time I saw particle filters. This is, so those of you that haven't seen this, and there's kind of no reason why you would have done. These are I think about them as being little tracers that you use to monitor the environment, and you track them, and you're trying to selectively sample a complex environment by tracking these particles. And so it's this really kind of neat, hopefully statistically efficient technique to be able to understand a complex system. And I remember seeing it thinking like, wow, that's crazy and awesome at the same time.
Right. Totally, totally. So I think maybe what's I hope that you all, if it's not 181, everyone in this class has a similar moment that you do something and it just sparks like, wow, this is interesting, this is cool. In the class, we're definitely going to be focusing on opportunities for you all to get a handle on the concepts, as well as the math and all of that. The math is you kind of have to grind through, but thinking about the concepts. And to encourage that, we would actually like to kick off an activity with you all. So here's a question that's been out there about for some time about deepfake videos. And so I'm going to show you a couple of examples of what these deepfakes are, and then we're going to do some breakouts to talk about both how you might detect these deepfakes and whether are we comfortable with these? Do we have issues with these? And just get ourselves thinking before we get too technical, just about what's interesting, what's ethical, and just thinking about the problem. All right, so let me go ahead and share an example. And so as I'm sharing this, one thing I would like you all to notice, if you like to geek out in the way that I do, is like what's in the YouTube sidebar, because this is another example of machine learning that personalizes somehow to what you're interested in. But let's get started with this particular video.
My full-time employees, and they're building to survive on $8 an hour
Oh, shoot.
in New York City.
Sorry.
And foremost in all of our minds has been the loss and the grief felt by the people of Orlando. Most of us don't.
Sorry. That was the sound clear on that one? I think it
was. It was a little quiet. I think maybe you hadn't shared the sound.
Yeah, let me just, I realized that. Okay, let me do this better.
Hang with us all. A little technical problem. Here we go.
Yeah, no worries. Here we go. All right.
$8 an hour in New York City. And foremost in all of our minds has been the loss and the grief felt by the people of Orlando. Most of us don't get our health care through the marketplace.
So this is an example of a video that looks very much like Obama.
And what you should know is that thanks to the Affordable Care Act, your coverage is better today than it was.
And this one kind of takes it apart and shows you what's going on. Here's another example of a video that's also quite convincing. And you'll notice that part of the tools that they use is to make it look old, but the deepfake itself is also pretty good. So this is a fake. This is literally fake news about what would have about Nixon describing the moon disaster when the astronauts did not make it back from the moon.
Good evening, my fellow Americans. Fate has ordained that the men who went to the moon to explore in peace will stay on the moon to rest in peace.
I'm not going to continue. So in both of these videos that we are seeing, they look fairly convincing. At least I find them fairly convincing. So here's what we're going to do. We're going to give you all about 5 minutes to go into breakout rooms. And in your breakout rooms, I want you all to discuss two things. First of all, how might you detect a deepfake video, right? Like, were there things as you were watching this video that would, let you know that this thing is not real? The second thing that I'd like you all to think about is, do you have issues with any of these videos, or under what conditions might you have issues with these videos? And what we're going to do after, again, about 5 minutes is we're going to regroup. We'll chat about how we might detect deepfakes, and then we'll talk about some of the ethics involved as well. So the breakout rooms are created.
And they're all open. And just a note on the breakout rooms, we have open rooms and rooms. So if you want to hang out with some people you know, you should go to a room. If you want to hang out with anybody, you should go to an open room. Of course, if you go to a room, you should feel free to stay there as well. So go ahead and join the
Yeah. This is an experiment, by the way. If everyone hangs out here, next time we're just assigning you to rooms.
And if you have the latest version of Zoom, you should be able to find your way into a room. So go ahead and join a room. We'll bring you back in 5 minutes.
Yep.
The rooms are open on my screen, but maybe that's just me.
A bunch of people don't see how to get into the rooms. Nari, do you have any advice about, I mean, on me, it's just the breakout room button.
Yeah, it's just at the bottom of my screen.
I also updated it today, and I don't have any breakout room thing sort of apparent.
Can we try a close and a reopen?
Yeah, we can try that.
I'll also. Can you all see it now?
No.
Okay.
I just see a please wait to be assigned.
Okay. I guess the breakout rooms are not going to work, Finale.
Yeah, let's.
We'll have to set them up differently next time.
Right. Supposedly the newest version of Zoom allowed people to choose their rooms, but all right. Well,
I think
hopefully people have had a little bit of time to think, or while you're also trying to figure out your breakout rooms. Does anyone want to raise a hand and share how we might detect? And like, was there something funny about any of these videos that you would be able to know? Hey, maybe it's not real. All right, Chloe, do you want to share your thoughts?
Yeah, I thought the most obvious thing was the mouth. Like, if you look really carefully, you could sometimes see it wasn't like properly synced up.
Yeah, absolutely. Let's get a few more. Joshua?
I couldn't really see it in these deepfakes, but usually when I see deepfakes like around the eyes or like the wrinkles of the eyes, don't change as much, and there's like less emotion.
Yeah. Matt?
Yeah, there's a certain level of, I don't think I could really tell graphically because it's like getting shared over Zoom. So whatever like increased fidelity that I might be able to tell the difference of usually is kind of lost for me. So
and that can be a bit of strategy, right? If you don't have too much resolution, it becomes harder to tell.
Right. So there's a certain level of like visually, I couldn't actually tell the difference, even though I think in the past I've found that with most deepfakes, obviously better ones, I might not have come across, but with most of them, I could tell the difference like just by taking a close enough look at them. But I think there's a certain level as well of just like what people are saying, oftentimes in deepfakes is something that like, I don't know, I've gotten kind of accustomed to fake news existing. So most of the time when I hear something, I'm thinking like against an internal filter or whatever, like, hey, is this something that
that's real?
I know happened?
Yeah.
Although I will say that the first one felt like it could have been something that Obama would say. Like, I totally imagine that Obama would expunge how much he loves the Affordable Care Act, right? So maybe that one would not have triggered the same reaction.
Nari, were you adding something?
Oh, I think I fixed it.
Oh, for the, okay. Well, I think for today, we'll just go with this. But that's great. We'll use that for next time. Let's get one more. Owen?
Yeah, I was gonna say that it's these deepfakes sometimes don't always accurately reflect the speech patterns, right, of these people. So if you, for someone like Obama, if you've heard him talk a lot, then you sort of know that one of his speaking tics is that he tends to pause a lot in the middle of his sentences, and like that deepfake, for instance, didn't really reflect that. Sort of not as a little bit more continuous than Obama usually is.
Absolutely. Yeah. So these are all really great points. And one thing that we're going to have this semester that we're quite excited about is this additional optional, but hopefully you all will enjoy, series on modern machine learning, deep learning, optional sections. And one thing to think about there, one thing that you'll see there is that, you know, deepfakes are kind of a race, right? Like you make something and people point out all of these things, you know, the eyes don't look good, the voice patterns don't match. And there's these techniques called generative adversarial networks who actually use this idea to try to, you know, basically one side is the side creating the fake and the other side is the side that is trying to detect the fake, and they play with each other until you get something quite convincing. So, you know, the fakes today are of certain quality, they'll keep getting better and better, right? So if you're like, okay, I know I can detect it based on the eye, that might work today, but it may not work tomorrow or some other time. So now what I'd like to do is just share a couple of examples of other forms of like impersonation that, or, you know, editing that are not deepfakes, and use that to chat briefly about, you know, how do we feel about deepfakes? You know, are these something that is like new and threatening, or is this just kind of old hat? And if it is new, what makes it new? All right. So that's a question I want you to have in mind as I show the next set of examples and videos. So here is a video of, sorry. Moving a few. Okay. Here's a video of a Russian robot that turns out to be a man in a suit. So this is not a deep fake. This is a fake, a person in a suit. And I just want you to take a look at it, see what you think.
Media, people raise questions about the dancing robot, including why it had.
Oh no, no ads. Okay, we're gonna skip this one. Here's another example that I think is quite fun. This is from the recent election. So the first one was a dancing robot. That someone was just a robot dress. Sorry, a person dressed in a robot suit. So that is an example of a fake that is, you know, didn't require any special technology, just required, you know, a costume. Here's one that does use a bit of technology.
Biggest mask I've ever seen. The biggest mask I've ever seen.
Will we ever get back all the jobs we lost? Or should we set up 11 million Etsy shops?
My economic plan would create $1 trillion in economic growth. He has no intention of making it better for you all at home. I brought back football. It was me.
What?
All right. You get the picture. So much better version of the first debate than the real thing. So here's an example of people's audio being adjusted, clips taken from the first debate that happened. You know, and these are examples of manipulation that, you know, again, are not deep fakes. Some involve technology, but are quite different. I'll give two more examples, and you know, that are just images. You know, so these are not even videos. So what we have here, you know, is a very famous picture of a Loch Ness monster that people thought were real for a long time, and also a very famous photo of Stalin removing one of his close people after falling out, right, from the video. Sorry, from the image. So there's lots of, I mean, this idea of like faking stuff is very much not new. So I'm curious to hear from you all. You know, what is it that makes that, you know, are we more concerned about deepfakes than any of these other things, or are deepfakes just yet another form of, you know, Photoshop and manipulation? David? Chen?
Yeah, so I think the biggest change here is really just the change in accessibility. Because like I think faking things has of course existed for a really long time, but the fact that like we have things like social media today that can sort of spread things like deepfakes where people don't know if it is really quickly, and like it's becoming easier and easier to fake these things. That like those two things together, I feel like really exacerbates the problems that can come about.
And if I can summarize that back, I think you're pointing to two kind of very important and distinct issues. One is the fact that it can be spread in a way that is much more efficient maybe than in the past. And the second is that it can be created much more easily. Alexander?
Yes, I was going to say that it also kind of moves the border of what's believable and what is no longer believable as like solid evidence. Because previously we would be certain that the video evidence is like 100% true, and now we can no longer be certain about that, and that kind of kills all the evidence-based reasoning that we can do for
that was
the
previously
purposes of the
considered
court.
sacrosanct. Yeah.
And we do not know where the new source of truth is. Like, what is more believable than the video?
Right. Yeah. So just to keep things moving, I think these are both really good points, or collections of really good points. And I just want to really highlight the accessibility issue. There's been a fair amount of media in the news about deepfakes as a political problem, right? That we can have Obama saying something that Obama didn't say, for example, and we can spread it to unwitting, you know, parts of social media who are now going to suddenly believe that, you know, he said something. But actually, one of the biggest uses of deep fakes has been in revenge porn, right? So this is not like a political thing. This is where someone, because it's so accessible, is allowed, or it has the ability to, you know, take advantage of someone else by, you know, putting people's faces onto pornographic videos and sharing them either on social networks or with friends or whatever it is. And kind of once seen, it's very hard to unsee. So I think that's important to keep in mind also, that, you know, accessibility of these tools can allow for all sorts of uses. And some of them are big and national and political, but there are other ones that really can also deeply affect, you know, the fabric of social relations in society. And on that note, you know, again, you know, the ethics of this stuff is really important because once we put a tool out there, it's unclear like how people will use it, right? And so as we're doing that, you know, how are we going to get there, right? This seems complicated. You know, creating these amazing machine learning tools is hard, but also thinking about their implications, that's also hard. And so what I'd like to start out by saying is just that I see there's like kind of two aspects to what we're going to be doing in 181. And the first part I'm going to, you know, dub the Zen. And that's not only thinking about the ethics, but also thinking conceptually, like thinking about what are the appropriate model choices, having the understanding that when you hit a new model or new technique, you have the framework to be like, oh, I understand this sort of thing makes sense to me. Thinking about where errors might happen, because errors, you know, may be innocent and, you know, may not be, right? There might be major safety issues, major ethical issues that come from these errors. And how do we evaluate to find those errors? So these are things that, you know, I really hope that people will get out of the class, that I want you to focus on in the class. That's not to say that there won't be some push-ups involved. You know, there's derivations, and derivations get messy. But what I really hope is that folks will think about the ethics, the model understanding, the concepts, all of these things. And then, you know, your push-ups have a place, you know, they have a context. And with that, I'm going to hand it off to David to continue with, you know, less ethereal notions of what's going on with the course and some actual concrete context. and logistics.
Thanks, Finale. Go ahead and let me share. Great. All right. So as Finale said, I'm going to talk about some of the more concrete things that we're going to do and see. Here's a taxonomy of machine learning. I think it's a good way to think about the space of things that we're going to see together. Right? So we've got supervised learning, we've got unsupervised learning, and we've got reinforcement learning. Let me talk about supervised learning first. And I just want to help you read this picture. The blue arrows here are train time. So at train time, you have a definition of a task you're interested in. You have training data. Here we'll typically use X to describe the features that correspond to the data, and Y to describe the target of learning. And then we'll have a metric that we're paying attention to when we train. And then what do we do once we've trained and this is called supervised because we're feeding this kind of target value. Think about this, if you're predicting cats and dogs, this image is a cat, this image is a dog. And then at test time or at runtime, I feed it a new image and it makes a prediction. Yeah, it's a cat, or with probability 0.8, I think it's a cat. So there are two variations on this. There are regression problems, which you probably have a high-level understanding of what a regression problem is. It's just one-dimensional, of course. Try to think about this as being very high-dimensional. It gets harder to think about. Here, this is X against Y. One example of this is Virtu Financial. It's a NASDAQ firm. It's one of the largest high-frequency trading firms in the world. They also think about themselves as market makers. So they're basically making trades very rapidly, like extremely rapidly in the stock market. And they have a prediction problem. They're trying to predict the stock price, often in the very short term. You can think about that as a regression problem because the target is a number. Okay. You can also have supervised classification problems. And actually, my cat-dog example is a better example of a classification problem than a regression problem. Think about regression as trying to predict height or price or something like that. So here are my cats, here are my dogs. And a nice example of this that we're all familiar with today, but we probably don't know that it's called QuickPath on iOS or glide typing on Android, is this nice UX feature where you slide your fingers around the interface, and it's using a language model behind the scenes. So it's not just looking mechanically at the digits and the letters that you drag your finger over. It's understanding the word that it thinks you're trying to type out or swipe out in the context of the sentence that you've described so far. So it's this classification problem. There's a set of target labels where the labels are words. Unsupervised learning, here's this picture again. So now again, this is, think about this if you want as the work you do informally. We could think about this as training time still, where we're trying to understand the right unsupervised method to use. The crucial thing here is that when we're doing unsupervised learning, there are no Y's, there's just data. There's just X. X is, again, the features or the content. There's no expert who has gone in and said, this is a fake story, this is a real story. And then you feed your unsupervised learning system that data, and you want it to deliver to you a summarization that you can understand in some way that hopefully helps you to gain understanding about the problem. Two types of unsupervised learning that we'll talk about in this class. One type is clustering, where you're trying to find these natural groupings of examples in your data, where you want a cluster to be a set of examples that are more alike each other than they are alike things in other clusters. Example of this would be Google News. It wouldn't be a very good Google News system if you went to see the news and every story that you saw was about the same topic. You don't want to read 100 stories about what's happening in Russia or about what's happening with the impeachment. So what Google is doing behind the scenes is it's clustering. It's bringing together stories that are alike, again, using language models, and again, without any supervision. Another example is embedding, where you're taking data and you're trying to embed it into a lower dimensional space. So here I'm showing you the data, which is the blue data, and I'm trying to find a lower dimensional space, in this case, this line, where you can see the data has been projected onto the line, and you're trying to find a lower dimensional space that captures the variation in the data. So if you squint at the blue examples here, you can see that the variation tends to be up and right. And so that's a sensible embedding if you want to find a lower dimensional way to understand what the data is. And we'll be talking about how to do that. I want to give you an example. This is example of point of sales data from supermarkets. You can see 2006 through to 2015. This is showing the sale of beer. And notice these are log scales. So how much beer is sold in these particular supermarkets in the US, how much wine is sold, in particular foreign wine, and how much cat food is sold. And you can kind of squint at this, and probably this is July 4th each year, where there's a lot of beer being sold. Okay, you can see generally there's a downward trend in consumption of beer for whatever reason, and there's a downward trend in consumption of wine, at least for foreign wine. And you can see that there's a spike in the sale of wine every holiday season. And cat food, who knows what happened here? There was a lot of cat food purchased that particular day. And the question you might have is, can we see the effect on demand of the 2008-2009 financial crisis? And of course, by looking at these time series, no, you absolutely cannot. But suppose I give you these time series for each of these 1,073 products in different locations, and then ask you to embed that into a lower dimensional space. And you run what's called principal components analysis, which is very much like the embedding picture that I showed you earlier. And each of these components, and think about kind of mixing together these components to recreate the original data. So in my picture, it's like you take the orange line and then you would mix in something orthogonal to that. And if you look at these, you do indeed see that one of the components is picking out 08-09 financial crisis, and it's this component here. So showing you that by using embeddings, you can learn something about very complex data. All right. Lastly, we'll be talking about reinforcement learning, where the training data for reinforcement learning is a sequence of state, action, reward. State, action, reward. You want to make this concrete? Imagine a robot rolling around Cambridge. The state is, where is the robot in Cambridge at the moment? The action is the next thing it does, and the reward is the utility, the happiness or the sadness it gains from taking that action in that state in the environment, right? This is reinforcement learning that you can think about it a little bit as if the rewards are the targets. What you're trying to find is you're trying to find policies that control, in my example, the robots moving through the city. And then at test time, at runtime, the prediction problem is, okay, here's a state. What do you want to do now? And that's what the policy will do for you. And that's reinforcement learning. Here's a video of a robot. This is a famous video, by the way. There's a robot learning to flip a pancake. And I'm not sure how many of you have tried to do this. I used to do this when I was a kid. We'd have pancake day, and you get the batter and you pour it into a pan and you try to flip it so you catch the pancake again. Now, this is not going to actually be a pancake. It's and if you saw that, it's like this kind of artificial thing that looks like a pancake. This guy here, who's an Italian AI researcher, is going to, first of all, physically demonstrate to the robot system, to the learning system, how to flip the pancake. Okay, so he's demonstrating this at the moment. And then after 3 trials, it's not doing so well. After 5 trials, it's still not doing very well. After 10 trials, it's still not doing very well. At this point, I think the research is not really paying attention anymore. He's kind of given up. 15 trials, still not quite doing it. So what's happening here is it's understanding the state. It's doing that through this motion capture. And it's gaining reward feedback. Did I successfully flip the pancake? And look, it's doing it now. It's pretty awesome. And remember, this was about 10 years ago now. So after 50 trials. And I would just point out that that speed of learning in this case was helped by the initial demonstration of the AI researcher in this case. Here's another example of what you could imagine doing through reinforcement learning. This robot just starts walking. This is Boston Dynamics, big robotics company in the Boston area that's developing these humanoid-like robots. This robot has decided to run away. And now it's walking through snowy fields, and at some point it finds a friend, and the friend will walk the robot back to the factory where it's supposed to be doing work. That same company, this is kind of just for New Year this year. Yeah, so that gets kind of wild. And actually, unfortunately, no, that is not quite reinforcement learning. So they were asked, are you using reinforcement learning? He said, well, no, not really. We're currently using control theory, but we plan on using reinforcement learning in the future. So it's also, I like this example because it gives you an example of, gives you a sense of where the field is and what we can do and what we can't do. So here, reinforcement learning would be too fragile, let's say, of a technique for these very expensive robots and maybe dangerous robots, right? These can physically lift a lot of things. So here's a cube. We structure the work that we do in 181 through this cube. We'll be thinking about supervised learning, unsupervised learning, discrete problems, continuous problems, non-probabilistic approaches, and probabilistic approaches. And then also graphical models and reinforcement learning. How we get there, course structure. I'm going to go through this relatively quickly because it's in the syllabus. We'll follow the cube. We will also spend time on excursions to talk about model classes, model selection, evaluation. You might be wondering what a typical lecture will look like. So a typical lecture is going to be chit-chat between me and Finale. And then we'll break up the session into 2 sessions. There'll be a little short break in between where you can hang out in breakout rooms and chat with your friends or make new friends. And then there'll be concept checks at the end. We'd love you to join us for live lectures if you can. Logistics, we would like all of you in particular to make an effort to attend 7 of our live lectures. We will give out exemptions. There'll be a form for you to explain why you're not able to do that. There will be 6 regular bi-weekly homeworks that will be done. They'll be due at 8 o'clock on Fridays. These are done individually. They have a theory component and a programming component. There's one practical, which is a more applied exercise. So you'll have a week to do that. You can work in a small group. There'll be 6 late days, but at most 2 late days per problem set. We're planning 2 timed closed book midterms that will be proctored over Zoom. There'll be weekly sections. There'll be section 0 this week. You already heard about the Beyond CS-181 sections that are optional. Lots of office hours, almost all of them on Collaborate. We're using Ed for questions and discussion, and there's more. There'll be concept checks, there'll be lecture recaps. There's a textbook available as well. So this week only, I'm not gonna spend more than a second on this because we've posted it onto Ed, but we're having office hours of these times this week only. And we're having special section 0 kind of math intro math intro sections this week as well. You can find this information on the webpage. Please pay attention to the collaboration policy. You can work with others, but the write-up must be entirely your own. And in particular, we want you to include the names of anyone you worked with in your write-up. Do not copy parts of other people's assignments or jointly type up an assignment. You can use textbooks and online sources, but you must also cite the sources. And do not look up solutions to specific questions from friends or the internet. You might be wondering if this is the right course. If you're looking for rigorous conceptual grounding, we've been showing you fun things and we'll keep doing that, but we're also going to give you a rigorous conceptual grounding in the foundations of machine learning techniques and how they work and when they don't work. And if you're looking to get an understanding of that, this is a good course. If you're looking for mainly theory, then Lucas Jansen's 195 in statistics is a good course. Mostly practice, the data science series is a good course. More depth than breadth, you could consider some of the 200 level courses. Can you audit? Yes, you can do all of these things. We'd be glad to have you. Do you need the prereqs? You need to be comfortable with programming. You need to have a comfort level with probability, with calculus, and with linear algebra. So it's up to you, of course, as to whether or not you need the prereqs, but you should have a comfort level with all of these things. We've made a very complete and I think very useful math review resource available on the website. And there are other resources that we'll make available as well. I do want to say that I think if you open this up, it may look a little daunting. I don't want you to think that you should just be able to open it up and kind of immediately remember or understand everything, but use that as a resource, and it will certainly give you a good idea of the scope of math that we might be touching on as we go through the course. What I want to do just in kind of wrapping up, and then we'll go to a short break, is this is fascinating. This is a episode of a series that was made by CBS in 1961, in this case to celebrate the centennial of MIT. And what you're going to see is you're going to see a screen actor named David Wayne speaking with an MIT professor named Jeroen Wiesner. Again, this is 1961.
The Thinking Machine.
Hello again. With me tonight is Professor Jerome B. Wiesner, Director of the Research Laboratory of Electronics at MIT. Dr. Wiesner, what really worries me today is what's going to happen to us if machines can think. And what interests me specifically is, can they?
Well, that's a very hard question to answer. If you'd asked me that question just a few years ago, I'd have said it was very far-fetched. And today, I just have to admit, I don't really know. I suspect if you come back in 4 or 5 years, I'll say, sure, they really do think.
Well, if you're confused, Doctor, how do you think I feel?
We're just really beginning to understand the capabilities of the computers.
I've got some film to illustrate this point, which I think will amaze you. Daniel.
Okay, so you know they were hopelessly optimistic I think we're still not quite at the point where we will say that machines can think, but I'm personally pretty bullish on how rapidly I think we'll see AI and machine learning continue to progress. If we had a little bit more time, we would have let that video play. The thing I'll leave you with before the break is that that video ends with Arthur Samuel. And Arthur Samuel famously in 1952 showed that through self-play, there's kind of a preview of AlphaZero. Through self-play, you can learn to, in that case, play a game of checkers. So somehow intelligence emerges in a completely non-supervised way. So we're going to take a 2-minute break. Let's see if the breakout rooms work. Hopefully you can go and hang out there for a couple of minutes. And then we're going to do some technical discussions for the remaining 20 minutes or so of class. So we're going to open up the breakout rooms. And Nari thought that she'd figured out how to let you go into them. So let's see if it works. But if it doesn't work, we're on a 2-minute break anyway, and we'll restart soon. Yeah, I guess it's not working still, Nari. And I think I know why. I think it's the way that I set the breakout rooms up at the start of class. So we'll be able to fix next time.
If folks need to just take, another 60 seconds, whatever break that you need to take, just go ahead and then I'll get started in just a few. All right, so let's get started with the first now technical part of 181. And as I go through this, I'm going to try to keep track of hands raised and such. I'll be honest, like I normally say that the two things that are the bane of my lecturing are like negative signs and transposes. And now with Zoom, it's like negative signs, transposes, and like screen management. So if I don't notice you right away, feel free to shout out. But let's try to focus on raising hands, and then I will try to call on folks. All right. So as David mentioned, we're going to be organizing the work that we are going to be learning throughout the semester into what we call the cube. And for the first half of the semester, that's really going to be the square, which is this notion of supervised learning, that there's going to be some inputs X, and every input X is associated with some output Y. And the goal is always going to be that given X's, we want to figure out what are the outputs Y. And we're going to divide these into 4 cases. There's going to be situations where the Y is continuous, and that's regression. Cases where the Y is discrete, that's classification. And we're going to look at this with both non-probabilistic and probabilistic methods. And so today, we're going to talk about one method that sits right here. It's a regression method, and it's not going to be probabilistic, right? So that's where we are. And if you want to look up more in terms of sections in the CS-181 textbook, what I'm talking about right now is covered in section 2.1 and section 2.2.1. All right, so how might we solve a regression problem? Let's just draw a cartoon of what a regression problem might look like. Here are some data points. Here's X, here's Y. And given some value for X right here, X, let's call it X test. We want to figure out, what should our prediction be for Y? So what to predict for Y. And over this lecture, this part of this lecture and the next lecture, we're going to talk about a couple of these non-probabilistic ways of doing this. And the method for today is going to be one of the simplest ways that you might imagine doing this. And that is, why don't we just look around this particular, this particular value, and we see that there's some data points here, right? And if they have nearby x's, so these data points have x's that are sitting kind of right around here in the training set, then maybe their y values, which are sitting like right around here, are good y values to propose for this particular x test that we have. So that's the core idea. This is called a non-parametric method because it scales with the data. We're not saying that it has to be a line, and we're not saying it has to be a specific type of curve. We're just saying, look at the points that are near to your point and make a prediction based off of that. So this is more formally called K. So this is going to be method 1 that we're going to talk about right now. K nearest neighbor, or KNN. And then again, the idea is going to be quite simple. So we have a data set, and the data set is going to consist of pairs of inputs and outputs. Sorry. All the way out to xn, yn, right? So this is our training data. And given some input x that we want to make a prediction for, we're going to first find k x of i's that are closest to our x that we want to predict. And 2, we're just going to take the average. So we're going to predict that this like y hat of x, right? This is our guess for y, what we think the output is going to be, is going to be equal to 1 over k sum over y. I'm going to index this with little k over here. So k equals 1 to big K, however many nearest neighbors we're going to look for. And implicit is that these are the K nearest xi's to our x, right? So again, in pictures, it's quite simple. If this was our test point over here, we found some values that were close by. And for the x values that were close by, we computed their y values over here. And we're just going to take their average to be the output. So this is a very, very simple technique. Let's think about it, right? Like I mentioned at the beginning, that the most important thing that we want you all to do is to really think about the zen of this whole machine learning endeavor. It's not just a bunch of math or equations. So what is this going to do? Like, when is it going to work? When is it not going to work? And you're going to be exploring this in a couple of problems in your first problem set as well. So in terms of pros for this sort of thing, it's very flexible, right? I didn't have to say that the data come from a line or that they come from a curve, and just whatever the data happen to have as their particular natural shape was what we went with, right? And so this is really great if it's hard to figure out what's the appropriate way to model the data. Some cons, on the other hand, might be that we need to keep the training data around. And if your training data set is really large, this might be a problem, right? So if you have millions, hundreds of millions of data points, you're going to need to store all of those. And once they're all stored, you're going to have to find the nearest neighbor. So every time you need to make a query, you're going to have to look through a potentially very large number of points, right? So let's add that. So expensive at test time. Now, I'm going to put a maybe over here because for those of you who've taken theory courses and systems courses, there has been a lot of work in terms of how to prune data points such that you don't need to maybe keep all of them, how to do really fast searches with the right data structures, all these sorts of things, right? So we're not saying that every time you put in an X, you need to do a linear search through like 100 million data points to find the closest one, right? That's just not how modern systems that would use a k-nearest neighbor would work. But it is a consideration, right? That if you just said that y is equal to wx, a line or something like this, you wouldn't have this issue. You wouldn't have this search problem. Another really important thing that we have to keep in mind, that may be a pro, maybe a con, but it's certainly a challenge, is that we need to define, what is near. And this turns out to be both the strength and one of the challenges of using this particular method. So imagine that now your data point X, I work on a lot of healthcare applications, is a whole patient's record or something like that. So it's a really complicated object. It has numbers, it has text, it changes over time. So figuring out even how to put that into a normal regression might be quite challenging, right? But maybe the doctors can tell you, two patients are similar to each other if they have similar ages, if they have similar diseases, if they have, similar blood pressures for this particular application. And then when you go in, you say, okay, well, I want to figure out what treatment's going to work best for me. Again, training a parametric regressor might be quite hard, but it might be relatively straightforward for you to search through the database and say, okay, who does have a similar age, who has similar illnesses, who has a similar blood pressure that I do, what treatments did they get, how did their treatments work for them, and perhaps that guides, what treatments I want to do, right? But if you didn't have those doctors to tell you that, hey, age is important and other illnesses are important, you might match on a zillion other things. You might have matched on gender. You might have matched on geography and said, my nearest neighbors are literally nearest neighbors, and I have picked out the people in the database that live on the same block as me. And that might not be the right metric in terms of being able to predict your health outcomes. So this is the pro and the con of this method, that if you have some insight in terms of how to do this first step, how to figure out the things that are closest, this can be quite powerful. But if you don't, this can be quite tricky. All right, so now I want to continue with one extension of this technique. And then we'll do a bit of discussion, more conceptual discussion about both of these. All right, so for this technique, so over here with k-nearest neighbors, we just averaged, right? We treated all of the y's equally. We said, if you're in my buddy group, you're my buddy group, you're close to me. There's nobody who's closer, there's nobody who's farther. It's either close or not close. And the idea here with kernelized regression is that we're going to be a little more flexible. We're going to relax that notion and say that some points may be more important. They may be closer than other points. The key, the name of the method that we're going to talk about here is kernelized regression. And the idea here is that when we want to make this prediction for y hat of x, we're going to take all the points in our data set, we're going to sum over them, and we're going to consider the similarity between our test point, so this is the point that we want to make the prediction on, and the point in the training set. And multiply that, so this is our weight. We're going to multiply this similarity by the value of this particular xn in the data set. So this yn corresponds to this xn. And we're going to normalize the distances or the similarities. So just conceptually, what's going on with this particular case is that, or with this particular example, is that if you have, for example, if you have an X who is really only similar to one other point over here, then right, sorry. Good catch. So if you have an X that is similar to really only one point in the data set, then this value is going to be large for only one point. It's going to be small for everyone else. So you're going to basically fit to one point. If you have a point that is close to many points and far from many other points, then you may select several neighbors. So let's draw that in pictures. So here we go. Let me push this up for the recording. So if we have a point, if this is our data set, looks something like this. And we have a point out over here that this is our X that we're trying to make a prediction of. It may be the case that there's only really one training point, this training point here that's close by, and we make the prediction just based on here. We're not going to collect any far away nearest neighbors, right? We're not going to say, oh, because I need 10 neighbors, I need to collect all these other farther points over here, right? We're only going to collect the one that's nearby. But if we had a point over here where we're trying to make a prediction, we might say that, hey, there's actually a bunch of close by points. Why settle for just 10 if there are 50 nearby points? I could get potentially a better estimate by averaging over all of them. So that's the key idea here, that this K is a notion of similarity. Just like we said, we need to define what is near over here. The secret sauce, the devil that's in the details, is all in choosing this in an appropriate way. If you have a good way of describing how similar points are with each other, then this is a very powerful technique. And if you don't have a good way, then it'd be, again, quite challenging to apply this. All right, so I want to pause for a second here. Are there any questions? And then we'll go on to, if there are no questions, then we'll go on to I have questions for you, right? Or thinking points for you.
Finale, there may have been a slight confusion over using K for the K nearest neighbors and then using K for the weight function.
Good catch. Okay, yes. Let me take that, and then Max, you can go next. So right, there's K. This is a bit of notational abuse, I guess, or overuse. So capital K, the function, K of x prime. Standard machine learning notation where K stands for kernel. And that's defined to be a similarity function. And then unfortunately, I guess, for this particular example, is that K nearest neighbors, which is also like, we don't say like M nearest neighbors or like Z nearest neighbors. Kind of convention is to say K nearest neighbors, where K is the number of neighbors that you are looking at. Yeah, we talked about being a little robust to different types of notation, and here we have it in the first lecture. So thanks for bearing with this. Yes, cool. Max.
Okay, so I'm just a little confused about in each of these two methods, the KNN and the kernelized regression, are we summing over all of the data points that are under a certain closeness threshold, or a set number of data points?
Great question.
The K nearest ones or something like that.
So in K nearest neighbors, we are summing over just the K nearest points. So our first step was to find these K closest points, and those are the only ones that we're including in the sum. So you can think of this as a hard threshold that says I'm going to expand out until I find, for example, if K is equal to 10, I find 10 neighbors. Once I find those 10 neighbors, I'm done. And those are the ones I'm going to sum over. The kernelized regression, on the other hand, let me be a little more explicit. So this is like little n equals 1 all the way out to big N size of the data set, is summing over the entire data set. Now, if a lot of points in the data set are quite far, so let's say I'm at this red X over here, then maybe K of red X to some xn in the data set is going to be quite small. small, for xn not equal to, let's, call this, this x near, right? So it may be the case that there's not very many that have large values, but you still are going to sum over all of them. Benjamin?
Yeah, in that expression for the kernelized regression, why does the summation on the bottom not cancel out the summation on the top?
Because we're multiplying by the yn. So this we take the product.
Oh, okay. Thanks.
Good question. Cool. I'm probably going to mispronounce your name. Ramim?
Hi, Graham. Yeah. I just wanted to ask one thing about the very last thing you said there about the similarity function outputting a small real number. Is it constrained to be positive, or could you have like a weight of 0 that basically gets attached to certain points?
Okay, great question. Yes, so we're going to do an entire section on what makes a valid kernel a bit later in the class. But for now, yes, treat it as something that is non-negative, because like negative similarities is a kind of funny concept if we just think about it conceptually. So they don't need to be normalized. It doesn't have to be between 0 and 1. It can be 0, and it can be as big as you want it to be, and that's why we have the normalization also.
Thank you.
All right, so in the last couple minutes, I'm just going to raise a couple of points to be thinking about. And these will hopefully be valuable for the homework problems in problem set 1. All right, so let's start out with this kernelized regression. And now I'm going to actually instantiate a kernel. So I'm going to say that k of x prime is going to be equal to the exponential of negative x minus x prime w, which is going to be a matrix, x minus x prime transpose. So what we're seeing here is basically we're taking squares. So w is going to be, let's start out with w being just the identity matrix. Right? So we can just ignore w, but we're going to keep it in there because we're going to use it a little bit later. So here is our kernel. So what this kernel is basically saying is that if you are, our notion of nearness is basically L2, right? Because W is I, we have x minus x prime times x minus x prime transpose. So this is the distance between these 2 points. And the negative of that distance is our, the negative, and then we take the exponential of that is our similarity. So distances are far apart, then this kernel expression will be small. And if the distances are close, right, we can do a sanity check and say, what if x is equal to x prime? Then this whole, the inside of this expression is 0, and this kernel is equal to 1. So this is going to be a number that varies between 0. Great. So we have this, and now let's think about, like, what does the role of this normalization in the denominator, right? Like, what is it doing for us, or what property does it introduce? And specifically, so like here's a thinking question, which is, what is the role of the denominator? Can we get values bigger than y max, smaller than y min? Oh, I see. Okay, this was already discussed, I guess, in the Zoom chat. Gotcha. Okay, great. Okay, good. So you guys already know that the denominator is helping this thing be an interpolator, I guess, and that with the setup that you have, you can't get something that is bigger than y max or smaller than y min because of this normalization that we're doing. So that's one thing to think about conceptually. By the way, I gave this complicated example of x potentially being like patience or something complicated. For 181 purposes, we're going to assume that there's a way to turn whatever data we have into a vector, right? So that vector could be the age, whether they have a certain disease or not. That could be encoded as a 0 or 1. But for our purposes, we're not going to focus too much on the problem of how does it become a vector, but let's assume that there's a way to turn the x's into a vector. So here's another question, just conceptual question to be thinking about. So let's say that we had a situation that looks like this, where we have some data out here, and then we want to make a prediction for some x that's sitting out here. How, what is it going to do, right? And there's something that you kind of want it to do if you see that there's like a line or a pattern, but you don't, but it's not actually going to do this, right? So we're about at time, but I want to leave this as a question for you all to think about. And in future lectures, we'll have like a formal concept check where we break out into separate rooms. Great. So any last questions from anyone? I'm going to leave this one open as something to think about. No. All right. Well, thank you all for joining. 136 people on the first day is amazing, and we are looking forward to an exciting term together.
There's a question, Finale, if you wouldn't mind repeating your final Q2 for those of you that want to be thinking about it.
Yes. Yes, happy to. So repeating the question is, what would our kernelized methods or the KNN make as the prediction for the point X, which was far away from all the other data points? And the relation, the kind of hint is that it's acting as an interpolator. It can't go beyond Y max. So it's going to have to find, what is it going to have to find? Who is it going to cling to?
Nari has also chatted it out. We'll be picking up parametric linear regression on Thursday. I see Jack Yan has an adorable cat, by the way. So that'll be Thursday. And we'll also spend a little bit more time there just kind of thinking through what all these objects are, right? X is a feature vector, Y is typically a scalar, etc. If you wouldn't mind, if a couple of you would try the breakout rooms, I think they should work now. It would be awesome so that we can be hanging out in them in future classes. I'm just going to open them. Let's see. Are any of you able to get into a room? Yay. Okay, perfect. So now you'll be able to have little hangout sessions as well. And we'll be able to do concept checks. So that's great. But this is the end of today's class. The videos will always be available quite quickly after class. Oh, and look at Jack's cat. That's so cute. Thanks all for being here today. I'm going to hang out as well. So if you have any questions, feel free to hang out.
Yeah, well, we can stick around for a few.
So cute. If you do have questions, feel free to either just raise your hands and ask, or you can just type into the chat. And when there are not very many, you can just shout out. Yeah, Tyler.
Hi, I'm very interested in auditing the class. Do I need to, I guess, email someone to get permission to the Canvas site if I'm no longer enrolled?
Yep, just email the course staff, email me, Finale, and if you have Nari's, email her as well, and she'll add you.
Okay, thank you.
Yep.
Attendance conflicts will be posted on Ed. We'll also send an email notification. It's coming. Don't worry. You haven't missed it yet.
True. So true. By the way, you can see some of the TAs here, those of you that are still here. Yash and Dylan, Ari, Kartik. Any other questions, Joel? All right, well, thanks for joining.